Hi, my name is Kimball Germane, and this talk is about how heap fragments can improve must-alias analysis for higher order programs. Let's start by considering procedure inlining, a fundamental program transformation used by optimizing compilers, and a client of must-alias analysis. Suppose that we want to inline the function call to f in the program shown. Well, our first task is to determine what flows to f. The value bound to f is produced by a call to process, and so it's not apparent what function we should inline. To determine which values to which f can be bound, we can use a control flow analysis. Suppose that a control flow analysis shows that only closures over the highlighted lambda flow to f. Next, we need to ensure that any free variables in the closure are in scope at the call. In this case, we have a free variable y, bound by an enclosing lambda, and this enclosing lambda also encloses the call to f. Syntactically then, it's sensible to inline this lambda at the call to f. However, is this operation safe? Let's consider a more concrete example. This program first defines a function g. G checks whether its first parameter x is 0. If so, it calls its second parameter h and returns its value as the result. Otherwise, it returns a closure which captures the binding of its first parameter x. This program then calls g so that x is bound to 42 and h is bound to false. The check for whether x is 0 fails, so g returns a closure over the current binding of x, which is to 42. The program then calls g again, this time binding x to 0 and binding h to the just returned closure. This time, the check for whether x is 0 succeeds, and g proceeds to call h. When we call h and invoke this closure, the result will be 42, and that will be the result of the program. However, a control flow analysis will show that at this point in the program, only closures over this particular lambda flow to h. This lambda has a free variable x, which is in scope. As before, it seems like we should be able to inline. However, by inlining the function and reducing, it becomes clear that we've changed the meaning of the program, for this x is returned only when guarded by a check for whether x is 0. Thus, our act of inlining has changed the result of the program from 42 to 0, and is thus unsafe. The issue that we failed to consider is that at the call to h, there are multiple bindings of x reachable. Because these reachable bindings to x are distinct, it was unsafe for us to replace a reference to one by a reference to the other. However, if these two bindings alias one another, it is safe for us to change a reference to one to a reference to another. This is why must-alias analysis is critical for an otherwise mundane optimization, procedure inlining in a higher order language. Going back to our initial example, we can see the same pattern of binding occurring. Both the call to f and the lambda, which captures y binding, lie within y's scope. However, as we have just seen, this condition alone does not suffice to prove the safety of the inlining operation. The solution to the aliasing problem that we build on is abstract counting. The abstract counting technique maintains a count of the number of concrete entities that a given abstract entity represents. When embedded in an operational framework, abstract counting is manifest as an enriched heap, which maps addresses not only to denotable values d, but also to account of the number of concrete entities represented by that abstract allocation. Abstract counting is capable of maintaining whether each abstract allocation corresponds to 0, 1, or multiple concrete allocations, represented here by 0, 1, and infinity, respectively. On the right is a heap enriched with abstract counting. Alpha naught maps not only to a set of closure values, but also to an abstract count of 1, indicating that this abstract allocation corresponds to one specific concrete allocation. Alpha 1 maps to a natural number n and also has an abstract count of 1, indicating that this abstract number n, although its value is unknown, refers to one specific concrete number. Alpha 2 also maps to an abstract number n, but its abstract count is infinity, indicating that its unknown value represents multiple concrete values. The operational framework in which abstract counting has been historically embedded has made it unable to maintain precision in the face of certain patterns of recursion. To see why, let's reconsider the initial example program, but this time in a recursive context. First, we will assume that this lambda is given a recursive binding. Next, we will assume that it calls itself recursively. In the body of the let, we have added a recursive call to loop, followed by a call to f, such that the results of each call are combined using the function combine. Let's walk through an analysis of this program to see this weakness firsthand. On the left, we have the program, where the highlighted portion of the program is the part of the program which has control within the analyzer. On the right, we have a model of the heap. In this operational framework, evaluation of each part of the program is performed with respect to the entire heap. We will walk through a zero CFA analysis of this program, meaning that the variables in the program and the addresses in the heap are in one-to-one correspondence. Although zero CFA, a context-insensitive analysis, is among the least precise of control flow analyses, the weakness we observe is present in context-sensitive control flow analyses as well. The first step to evaluate this LETREC is to evaluate the right-hand side of the binding. This creates a dummy entry in the heap with an abstract count of 1. This expression is a lambda, which is a simple expression, and evaluates immediately. We then proceed to the body of the LETREC. Now, the binding to loop has been resolved, and we can perform the call. As we perform this call and enter the function bound to loop, we allocate two new bindings in the heap, one for x and one for y. Because each of these bindings is new, they have an abstract count of 1. We will skip over the evaluation of the right-hand side of the let and instead proceed to the inner call to loop within the body. Notice before we make the call, though, that the binding for x in the heap has been removed. This is because this framework uses the technique of abstract garbage collection to remove bindings that are not reachable from evaluation from the heap. This increases precision. The binding for y has not been removed, however, because it is reachable from the function bound to f, and f is reachable from the continuation of the recursive call to loop. As we enter the call to loop, two new bindings of x and y are made. Because there was not a previous binding of x in the heap, the binding for x has an abstract count of 1. However, because the binding of y existed in the heap already, the new and the old binding are merged, and the abstract count becomes infinity, indicating that it represents multiple concrete bindings. What we have seen is that when we have a recursive call that is not in tail position, where some of the bindings of the function are reachable from the continuation of the call, that we completely lose precision with respect to those bindings. This diagram depicts the conventional operational model, an open expression on the left whose free variables reference bindings resolved in the entire heap on the right. We address the weakness of this operational model as it stems from the shared use of the entire heap by splitting the heap into fragments as evaluation proceeds, one fragment for each stack frame. This separation into fragments allows multiple bindings to the same abstract address on the stack, a hallmark of many recursive patterns, to remain isolated and allows abstract counting to maintain precision. To see how heap fragments fortify abstract counting, let's perform the same analysis as before, but this time with heap fragments. In this analysis, each expression and frame maintains its own heap fragment. The expression with control is the expression on the top of the stack. As before, we evaluate the right-hand side of the loop binding, a lambda, and proceed to the body of the letrec. In making this call, we introduce bindings for x and y into the heap fragment, each with an abstract count of 1. Up to this point, the analyses exhibit the same precision. Again, as before, we skip the right-hand side of the let and proceed directly to the recursive call to loop. Notice that the heap reference to y present in the previous analysis remains in the heap fragment for the call's continuation frame, but does not appear in the heap fragment of the call itself. Thus, when the call is made, both the bindings of x and y are fresh to the heap and enjoy an abstract count of 1. The analysis has encountered this precise configuration of expression and heap before, just 2 slides ago, which the analyzer detects to tie the recursive knot. In the end, we have a more precise account of aliasing, which allows us to justify inlining in the recursive context, and the analyzer has explored a smaller state space to achieve it. To maintain the stack correspondence necessary to use heap fragments, the analysis requires a push-down model of control flow, which is furnished by a so-called push-down precise control flow analysis. This shifts the operational model from one which models heap snapshots to one that models heap change summaries. This shift has a non-trivial effect on the abstract counting machinery, which we discuss in the paper. The use of heap fragments also allows us to instantiate a more general form of binding alias analysis known as binding invariance, which we recount in the paper. Because a heap fragment need only close an individual stack frame or expression, abstract garbage collection determines more bindings to be irrelevant, leading to significantly smaller heaps within configurations. This tendency should result in analyses which explore smaller state spaces and have more precision. Our empirical evaluation offers evidence that this is indeed the case, with many instances showing the effect dramatically. Thank you.